Alright, today we are going to be learning about the mole, which is a brand new unit in chemistry, and you're going to be using it a lot. I put the picture of the animal, the mole, here just to let you know that it's not the same thing. So let's get started. Let me ask you a question first. If you had a sandbox like the one pictured here, how could you figure out how much sand is in that toy sandbox? Is there more than one way that you could do that? Think about these options. One way would be to actually count the grains, count the number of sand particles in the box. That sounds kind of like a pain. Takes a long time too. Another option would be to weigh it. You could figure out how many grams or kilograms of sand were in there if you had a balance or a scale to use. A third option would be to take that bucket in the sandbox and figure out the volume of the sandbox. You could count how many bucketfuls of sand you got out of it. Really, all three of these are possibilities. Each one requires different equipment and different amounts of time. Some are easier than others. So it really comes down to a matter of which one you want to do. But you can find the answer to this question with any of these units by using conversion factors. And that's where the mole comes in. A mole helps us make these conversions. It's kind of like a measuring cup when you're cooking in the kitchen. If you measure out 1 cup of sugar or 1 cup of flour, you know what that measuring cup looks like when it's full of that material. But you know that the molecules of flour and sugar are different size and different mass. So you might not have exactly the same number of particles in each one of the cups that you measure out. And that's what a mole is like. Here's another analogy. It's kind of like the word dozen. When I tell you a dozen, you think of the number 12. Well, look here. The definition of a mole is 6.02 times 10 to the 23rd particles. A really huge number. But just like a dozen means 12, a mole means 6.02 times 10 to the 23rd. That number's in your reference packet. It's called Avogadro's number. So what are particles? Well, particles can be a couple of different things because remember, elements are made up of atoms. So particles can be atoms, but compounds with multiple atoms are called molecules. So particles can also be molecules. Let's take a look. You're going to have questions like this that are going to be conversions. We want to look at how many moles of magnesium is in 1.25 times 10 to the 23rd atoms of magnesium. Alright, so when you think about it, what type of a problem is this? What are you starting with, and what are we going to try and find out? Well, I think that we're starting with particles. 1.25 times 10 to the 23rd atoms. And I'm trying to get to moles of magnesium. So what I'm going to have to do is use this new term as a conversion factor. Remember how we work conversion factors in chemistry. So I'm going to work on the screen, and you should work this problem with me. We're going to write down what we're given first. So I'm going to write down 1.25 times 10 to the 23rd atoms, and then we have to convert it. So I'm going to make myself a space for that conversion factor. Now I know atoms has to cancel out, so I'm going to put it on the bottom, and I'm going to put moles on top because that's what I'm trying to find. The new conversion factor that I just gave you is that 1 mole of any substance is that Avogadro's number, 6.02 times 10 to the 23rd atoms. So atoms here cancels with atoms here, and I'm going to multiply across 1.25 times 10 to the 23rd times 1, divide by 6.02 times 10 to the 23rd. Now let's get our calculators and work that out. The answer that I got in my calculator was 0.2, and there's lots of numbers. We're going to round to 0.208, and it's moles. 0.208 moles of magnesium is the answer to this conversion. Now, if you did not get that answer, Make sure that you are entering this scientific notation in your calculator correctly. You may have to put this number down here in parentheses when you enter it into your calculator. See if that works, and if you still don't get this answer, I can help you next time. Alright, let's take a look at another one. This one is how many moles of sodium is 6.482 times 10 to the 23rd atoms of sodium? It's a different element, but still, it's a problem that we are starting with atoms and going to moles. So again, let's start setting up, we want to start with what we're given. Let me get my pen back here. I'm going to write down the given first. Now once I write the given, 6.482 times 10 to the 23rd, set up space for a conversion factor to go. I know that atoms has to cancel out, so I'm going to put atoms on the bottom, and I'm going to put moles on top. Now you figure out how moles and atoms are related. It's that new conversion factor again. 1 mole is 6.02 times 10 to the 23rd atoms. Squeeze that in there. I'm going to put this in parentheses just to help you remember with your calculator, because what's going to happen is that same math function again. We're going to multiply 6.482 times 10 to the 23rd times 1, then divide by 6.02 times 10 to the 23rd. So I'm going to type that in my calculator now. And when I get that all typed in the calculator, I get just over 1 mole as my answer. So I need to round that off to 4 digits. The answer I'm going to go with is 1.077 moles of sodium. So if you have 6.482 times 10 to the 23rd atoms of sodium, you have 1.077 moles of sodium. And that's actually going to be true for any element. It doesn't just have to be sodium. If you look at the way this conversion's set up, you'll see that. I didn't have to use anything specific for sodium to solve this problem. Let's keep going. Okay, so now let's write our given here. 1.03 times 10 to the 5th moles of cesium. And I'm trying to get it to atoms. So this time I need atoms on top, and I'm going to put moles on the bottom. The conversion is 1 mole is 6.02 times 10 to the 23rd atoms. Okay, so moles cancels with moles, and I'm going to multiply straight across here. So in my calculator, multiply that out, and the answer that I get is 6.20 times 10 to the 28th atoms. Now that seems like a really large answer, but think about that for a second. An atom is really, really small, so you would expect in this many moles, because that's like 100,000 moles, that there would be a lot of atoms. So this number is okay. It's fine that there are very large numbers. Let's try some more. In number 4, we've got moles of sulfur, and we're trying to convert to atoms, or particles. Alright, so let's set this up the same exact way. Write down the given. I hope you see the pattern that's forming here in terms of how we're working these out. 10 to the negative 3 moles. You write down your given first, make a place for the conversion to go, fill in your units next. In this problem, I know I need atoms on top because that's what I'm looking for, and I need moles to cancel. Avogadro's number goes here because I've learned that there's 6 times 10 to the 23rd atoms in 1 mole of any substance. So moles cancels with moles, and I'm going to multiply straight across here. 8.925 times 10 to the negative 3 times 6.02 times 10 to the 23rd. And the answer that I get here, let me write it over here for you. I got 5.0 1.373 times 10 to the 21st, and the units for that are going to be atoms. So when you convert moles to atoms or atoms to moles, you're using Avogadro's number every time. Alright, here's number 5. This time I'm starting with propane. I have a compound this time. I have 2.12 moles of it. I'm trying to convert it to molecules. So let's do a conversion factor. We're going to set it up using that pattern that we've been seeing. Write down your given first, which is 2.12 moles. Now this time I've got C3H8, propane, like the gas that you burn in your grill at home. There's my conversion factor. The unit that I'm going to need on the bottom is moles, and the one I'm going to put on top is molecules. Alright, so I've got molecules on top and I've got moles on the bottom. So how are these two units related? Well, you figured it out probably. In 1 mole, there's 6.02 times 10 to the 23rd molecules. So this mole here cancels with moles here. I'm going to multiply straight across 2.12 times 6.02 times 10 to the 23rd. And my answer here comes out to be 1.28, I rounded just a little bit, times 10 to the 24th molecules. Now I want to make sure that you notice on your calculator there are other numbers here. It's not just 1.28. We did have to round. Get in the habit of looking at the end of your calculator answer to find this exponent. Because if you only write 1.28 molecules as your answer and you forget the times 10 to the 24th part, that's very wrong. That number is a very different value than just 1.28 by itself. Alright, a few more. Alright, this is a two-part question. Actually, there's a review question there at the beginning. It wants to know, what is the name of this compound? So when I look at this compound, I think that it is ionic because I see barium, which is a metal, and PO4 is a polyatomic ion. So if you look that up in your reference packet, I think you can figure it out. The name of this compound is barium. Did you find PO4? Phosphate. No prefixes or anything like that. The second part is how many molecules are there? We're going to start with 1.75 moles of this compound. And when I take the moles of the compound and set up the conversion factor, I know that moles is going to have to go on bottom. And I know I'm looking for molecules. So I'm going to write that one on top. Didn't draw my line long enough. Okay. The relationship here is in 1 mole there is, you guessed it, 6.02 times 10 to the 23rd molecules. So moles cancels with moles, and you multiply straight across 1.75 times Avogadro's number, and the answer, remember look at the end for the exponent, is 1.05 times 10 to the 24th molecules of barium phosphate. So even though it's a compound, not an element, the way you set it up was really the same as all those other conversions. Okay, one more. This one's also a two-part problem. Now the conversion's first here. It wants us to figure out how many moles are in 1.5 times 10 to the 23rd molecules. Alright, let's work this out and see if your answer is the same as mine. I'm going to write down my given first. 1.5 times 10 to the 23rd molecules of this compound. And I'm going to set up my conversion factor. I need molecules here to cancel out. So I'm going to put it on the bottom. And I'm going to put moles on top. Another thing I'm seeing about this pattern is that it's always 1 mole. 1 mole is 6.02 times 10 to the 23rd. That's our new Avogadro's number definition. Since this number's on the bottom, I'm going to put it in parentheses to help you remember to enter it into your calculator correctly. You're going to have to do some division here. You're going to type in 1.5 times 10 to the 23rd times 1 divide by 6.02 times 10 to the 23rd. And you do get a long string of numbers here, but the molecules have canceled out. Our answer is going to be in the units of moles, and I'm going to put 0.249 as my answer. 0.249 moles of this compound. And then part B is the easy part. What is the name of this compound? This is one of those special compounds that has a common name. You find it in the kitchen in tons of cleaning products. Its common name is ammonia. So a little bit of review with the naming, but mostly I want you to practice getting the pattern down for setting up these conversions and using your new conversion factor, which is the mole, being equal to 6.02 times 10 to the 23rd particles. We'll work some more in class next time. Bye!